We are actually down to 3 speakers instead of 4. Unfortunately, Geronot Wagner was not able to make it today, ironically, because his flight was canceled due to all the weather-related activities from climate change. So that's unfortunate, but we do have 3 great speakers, and we'll have a little bit more time for them. They can take their full 20-minute sessions. So this first speaker we have this afternoon is Mark Rosengrant. Mark is the Director of Environment and Production Technology Division at the International Food Policy Research Institute. He has extensive expertise in research and policy analysis in agriculture and economic development. The emphasis of his research is on water resources and other critical natural resources and agricultural policy issues. His presentation title is Climate Change Impacts on Agriculture and Adaptation and Mitigation Policies to 2050. Dr. Rosengrant.
Okay, well, thanks very much. It's great to be here. So let me jump right into it. So what I'm going to do is, as I said, I just very briefly look at climate change impacts on agriculture and at a high scale, and also to reintroduce the topic of the big impacts agriculture has on climate change. Then most of the talk will be about some analyses that show different kinds of policy investments and technologies as potential adaptation or mitigation instruments. Among those, I'm going to look at specific climate-smart agriculture technologies. That's become a buzzword that's widely used at least in the ag policy in developing countries that I work at. And then also broader agriculture investments such as agriculture research, infrastructure, and roads and irrigation. And then I'll look, instead of the supply side there, I'll also look at the demand side and how you could have influenced well-being and greenhouse gas emissions through demand side policies as well. Then I'll talk a little bit about some policy implications. The general class of modeling that I'm going to be using here is pretty widely in looking at global impacts of climate on agriculture. You start, of course, with the global general circulation models that determine temperature and precipitation scenarios over time. And we've been hearing all about the RCPs on several topics here in the last couple of days. And then we look at how those kinds of changes in temperature, precipitation, solar radiation, and other factors affect crop and livestock yields through globally gridded crop models and also some biophysical models of livestock production. In turn, we can feed those kinds of biophysical shocks into global economic models, and those then allow us to look at how changes in area, yield, consumption, trade, and other agricultural factors occur over time. We can then also link those kinds of outputs to coordinated models to look at further at how those in turn influence food security and global greenhouse gas emissions. When we look at the biophysical impacts, and we've seen a number of slides similar to this kind over the last day or so, you get fairly large impacts in many cases on crop yields due to climate change. This is using the Hadley GCM at RCP 8.5, and the estimates are made at a globally gridded basis using the DSAT crop models. You can see here you get very large impacts globally, as much as 30% lower maize yields relative to what it would be in 2050 without climate change. So those look pretty scary. But then if you run those biophysical impacts through...
I'm sorry,
what's
your
happening?
Slides are actually not advancing.
Oh, great. Okay. I'll definitely need my time now.
Let's see here.
Maybe there's a slideshow up here.
So if we have any technical assistance in the house, our slides aren't advancing.
Thanks very much. Okay. Thanks. So, let's say so I'm going to look at impacts of climate change on agriculture and in turn on climate change. Then I'm going to look at a series of analyses of how policies, investments, and technologies can influence those outcomes, and then look at some policy implications. It's going to be using, as I said, a class of models that combines general circulation models with globally gridded crop models through to global economic models, and then on to looking at food security, greenhouse gas emissions, and so forth. We get very big impacts, and we've seen that in a number of presentations. If you look at just the biophysical impacts of climate change through heat, precipitation, and other effects, this shows results for global maize on a globally gridded basis, as much as 30% decline in 2050 relative to what it would be without that. But then when you factor in economic responses to those biophysical shocks, the picture the negative impact is dampened quite a bit. This particular slide shows looking at 5 different global economic models that we collaborated with, including the impact model of IFPRI that I'll get into a little bit more later, and for coarse grains, rice, wheat, oilseeds, and sugar, looking at the impacts of different levels of climate change on crop yields, area, production, prices, and trade. So you still get some significant impacts, of course, from climate change in 2050, but now it's more on the order of 7 to 8% on average for the negative yield impacts, because when you get that initial shock due to the biophysical changes, that tends to push up crop prices. In turn, that induces some higher input use by farmers, and as you can see in the second bar, it also induces some increase in areas, because new areas can be profitable to grow crops. So overall, the total production doesn't go down nearly as much, but in fact, you still do end up at an equilibrium with higher prices, as much as 15% higher prices, and we'll see a little bit later that does have significant negative impacts on food security. You also see here you do get a positive trade impact through these shocks, and that goes back a bit to what Tom was saying, that under climate change, some areas get hurt more, and particularly Africa ends up not doing well, and ending up having to import more of these kinds of commodities, which again shows the importance of keeping open those the trade relations internationally, so that trade is available for import under climate change conditions. This shows up a bit. Just to point out again that agriculture also can be a very big part of the problem. If you look at the green area is land use change. These are world greenhouse gas emissions flow charts. It's a couple years old, but it's still, the big numbers are pretty much correct. So about 18% of emissions are due to land use change, which is almost all deforestation. There's also a direct impact of about 13% from agriculture, but then agriculture also likely accounts for at least half of the land use change problem. So agriculture overall is going to be something like 22 to 25% of greenhouse gas emissions. So it also needs to be part of the solution, as well as a sector that also needs help in terms of alleviating impacts. So let's look at what are the possibilities of doing better in the agriculture sector with respect to climate change in both adaptation and mitigation. First, we did a study where we're looking at global adoption of selected CSA practices. So this is sort of all the rage in the development community now in terms of looking at the potential for adapting to climate change. And we do find here we're looking at a number of different practices: no-till, integrated soil fertility management, alternate wet and dry rice production, and urea deep placement. And again, we're using a couple of different GCMs and RCP 8.5, and using the impact modeling and with the DSET crop model. And here we look just at maize, wheat, and rice. They account for about 40% of global crop harvested area, and looking at different levels of adoption rates. Here we show down below up to 70% for no-till and rates of 40% for the others. As we see here, we actually do find that we can get essentially triple win solutions. We get higher production, as you can see in the first row, reduction in food prices, somewhat of a reduction in area because you're producing more on lower area, and the price effect also helps to reduce area. You also reduce the population at the risk of hunger by about 3% in 2050, reduce the number of malnourished children, and increase, this is a reduction, reduce mean greenhouse gas emissions by about 20 million tons. That's actually a small number. Most of the studies you see look at needing $1 billion to $2 billion per year, so 2 billion million tons of CO2 equivalent per year from agriculture to help keep us to the 2.0 level. So that, again, they're small wins, but they are wins, so that shows potential for the future. Then we're also going to look at then broader investments to see if bigger levels of investments across a number of subsectors can do even better in terms of combining food security with adaptation and mitigation to climate change. Here we do use the impact modeling system linked to a CG model. It's the GLOBE CG, General Equilibrium Model. It's sort of in the same class as the GTAP model that Tom Hurdle described this morning. We can use this to look at a wide range of different drivers and policies, and can estimate a series of different outcomes, including sort of standard agricultural outcomes, but also employment and GDP in different sectors, as well as greenhouse gas emissions, water scarcity and quality, and soil carbon and energy use. This is utilized for projections on an annual basis. We cover about 130 countries, 64 commodities, and have integrated river basin models and hydrology models in it too, so that we can take care of those, looking at the consistency with the water sector as well. So here we're just going to show some quick results from alternative investment scenarios. In this particular result, we're going to look at 2030. We also have these out to 2050. So this uses the climate change scenario as a reference point, and then runs a range of scenarios with different levels of investments, with increases in investment beginning in 2015. And that includes research and development, particularly investment in genetic improvement in crop varieties. It includes investments in the water sector, including expansion of irrigated area, and also investments to improve water use efficiency. This is water use efficiency at the basin level. It's not the plant level efficiency that we were hearing about before, as well as looking at soil management. Then we also look at investment in transportation and energy sectors in order to benefit agriculture production and value chains. There's a wide range of results here that I won't go into in detail. The first 5 there are different levels of investment in agriculture research. You can see the first column is average annual cost. This is incremental cost over the baseline investments. The baseline investments are $43 billion per year across these particular sectors. We then show high irrigation and high irrigation with water use efficiency, and RMN is the investment in rural and marketing infrastructure. Let's just focus on some of the results for a comprehensive investment cost, which doesn't actually combine all of these, but it combines the highest result for irrigation together, for research and development, together with the investment in irrigation and water use efficiency, and the investment in rural infrastructure. So if you look at the bottom line there, the average cost of that is about $26 billion a year out to 2030. Again, that's on a $43 billion base. It results in an increase in GDP of 4%, which is, of course, a huge number, given the many trillions of dollars of global GDP. So you get huge economic benefits. It increases agriculture supply by almost 10%, reduces hunger, expresses the risk of hunger according to the FAO definition by about 31%, reduces the water use by 9% mainly because of the water use efficiency investments, and reduces greenhouse gas emissions by about 12% while increasing forest area by about a small percentage point. So you're getting the greenhouse gas emissions is significantly from reduced emissions from more efficient livestock production, but also from reduction of area expansion and reduction of land use change due to agriculture expansion. So you can get significant improvements both in food security, economic welfare, and while reducing greenhouse gas emissions. Looking here at in more detail at the results on hunger in 2030 according to investment scenarios. If we look at the world graphs on the left-hand side, the bars represent the population at risk of hunger, and the dots represent the share of hungry people. So if you look at the world, the first bar here is in 2010, then you see 2030 without climate change, assuming weather from the last 50 years. Under that situation, you can get from about 800 to about 500 million people. If you introduce climate change, you increase the number of hungry people by about 80 million. But then if you have this more comprehensive investment program, you can cut it down to about 400 million people, about half of the starting figure. So climate change does have a negative impact on hunger or increases hunger, while the investments can counteract that and actually improve it even relative to the climate change and the no climate change case. If you look at the percentages, globally it goes down, you can reduce percentage of hungry people from about 15% to 5%, and every region except Africa, which is south of Sahara, which is the third level, you get below 5% or at 5%. You still see large improvements in Africa in percentage reductions. Because of rapid population growth, the number of people hungry stays very much the same. Now let's look at the demand side. So here we have looking at climate change, nutrition, and health, and this is a collaboration between colleagues at Oxford and IFPRI to look at global health implications of changing diets and weight levels subject to production and the socioeconomic developments as well. So here we coupled the impact modeling that I already talked to you about with a global health model that was developed at Oxford that looks at estimates the health impacts associated with changes in dietary and weight-related risk factors due to consumption changes. So let's first look, this first slide here is looking at the climate-related deaths by risk factor and cause of death projected in 2050. This is only due to the dietary impacts of climate change. It doesn't look at infectious diseases and that we've heard about earlier, and in others it doesn't look at direct heat stroke related deaths. This is strictly for dietary composition. Here we look at a number of risks of diseases, including coronary heart disease, you see at the top, stroke, cancer, and then other chronic diseases combined. As we look here, that on the left hand, the total number of climate-related deaths are about 500,000 per year in 2050. And if you look at the second column, the biggest factor causing that is the lack of fruits and vegetables as the primary risk factor globally there. You can see the others, like underweight and have a lower contribution. If you look at something that seems counterintuitive, then under climate change, the number of deaths relative to a baseline case actually, due to obesity actually go down, and that's just because the prices are higher. People who have just moved into sort of the overweight and obesity class eat less and actually end up being less obese. So it shows the kind of complexity that you get when you're looking at the composition of diets, not just at calories, or for example. Then we wanted to look at, okay, given that climate change has these significant effects on health and on deaths, can you design incentive policies that would reduce those deaths and could also affect the rate of climate change as well? So here we looked at greenhouse gas taxes, or really should be called greenhouse gas-based taxes on food commodities at the point of purchase. And here in the first experiment, we looked at taxes implemented independently in each country and look at emissions and health impacts. And here we do it for 2020. We then, on this particular scenario, put greenhouse gas price of $52 per ton CO2 equivalent. That was associated with the discounting of future climate damages at a discount rate of 3%. And here we did first a flat tax across all commodities. Am I getting close? Yeah, a couple minutes. Then we also then experimented using various kinds of targeted taxes. For example, allocate revenues specifically to subsidize fruit and vegetable prices and subsidize the poor. A couple of quick things to see, the greenhouse gas taxes, even though they're on a uniform basis, they end up with a much higher incidence on those commodities that have the highest greenhouse gas emissions in their production and consumption. So beef, as you see, has a very high tax, followed by pork and other meats, and other commodities have very low taxes. The first thing to note, this kind of tax policy can dramatically reduce greenhouse gas emissions, again getting about a gigaton reduction in CO2 equivalent, as you can see for the world on the left-hand side, including about 2/3 less of that from less red meat and 1/4 from less milk. In terms of avoided deaths, if you look at the left-hand column, it's actually fairly disappointing. You get only about 100,000 avoided deaths if you look at the all-risk summation there in that column. And that's because taxes, although they reduce meat consumption, which is beneficial, they also reduce the consumption of other commodities as well. So you're losing the healthy commodities as well as meat. Under an optimal tax scenario, I'm sorry, rushing through these quickly. If you look all the way to the right, when you design it to have targeted subsidies to more healthy foods from the revenues from the tax, you can get those avoided deaths up to about 500,000, so counteracting the impact of climate change while also reducing greenhouse gas emissions. Some quick policy implications. I think one of the key things that we see is we really have to move to not looking only at adaptation and mitigation on the supply side. The demand side of food is going to be essential, and that meat is one of the key sectors that we're going to have to seriously deal with. Incentive policies are complicated, as we saw, but they can, with proper design, lead to significant benefits. Technological change in food, we've already heard about in vitro meat and meat substitutes could help, but it's too soon to see how much they're going to help. On the supply side, we saw that targeted technologies can help, but it's relatively slow. Bigger reductions in greenhouse gas emissions and food security can be achieved through broader investments in ag R&D, rural infrastructure, and irrigation. We also didn't deal with it, but eliminating subsidies on fertilizer, energy, and water would also have very big impacts on reducing greenhouse gas emissions, for example, by reducing nitrous oxide emissions from soils. And the other thing to start looking at, and let me have just one more slide after this, is decentralized information technologies, such as cell phone, weather, and crop information apps, small sensors and radios to make agriculture more efficient. And I'd just like to introduce that as really a wild card here is the potential for advanced agricultural technologies to really change the picture. if we look at it, there's obviously been rapid productivity growth over time in many crops, but in general, technological change in agriculture has been very slow compared to other sectors. At any given time, total factor productivity growth in agriculture is well below other sectors. But now, in fact, from a push from technological change outside of agriculture is creating potential for much more rapid change in agriculture. That's the new genetics, gene editing, synthetic biology, robot sensors, and so forth. And those could have a mixed impact, though. They might give big advantage to developed countries over developing countries. They also could be very disrupted because they could be labor and land saving, so you would use less labor and give incentives to create economies of scale that could put pressure to consolidate land ownership, pushing labor off farms. So there's a lot of socioeconomic impacts we have to look at, but I think there also are likely to be labor smart in terms of with more efficient, larger sizes of farm, you'd have less deforestation, lower food losses and value chains, and reduce fertilizer use to the efficiencies. So I think this is going to be one of the key uncertainties in the future for the agriculture sector. Thank you.
All right, our next speaker is Arun Agrawal. He is a Samuel Trask Dana Professor of Natural Resources and Environment at University of Michigan. His research emphasizes the politics of international development, institutional change, and environmental conservation. The talk today is going to be Everyday Adaptations to Climate Risks. How well do climate policies take into account what people do?
Thank you very much. There's a slight change to the title of the talk. Some of the work that we are doing on social protection in India, we were able to complete the research, and I'd like to present the results from some of this research as part of this talk. Thank you very much I should also say, I have to leave right after I finish my presentation. So I'm very sorry that I won't be able to take questions, but thank you very much for inviting me to do this talk. The talk that retitled it is Everyday Adaptations, Social Protection, Livelihoods, and Climate Resilience. It's a joint project with the International Institute for Environment and Development in England and a research group I coordinate, FLAIR, which is focused on forests and livelihoods. And the work that we are doing looks at a particular social protection program in India, the National Rural Employment Guarantee Scheme, which is the largest employment guarantee scheme in the world. Last year, it generated something like 2.5 billion person days of employment in India, covered about 60 million households, and has had, by all accounts, a very substantial impact on employment, on incomes, on nutrition, and a range of other local economic outcomes. In this project, we were looking at how social protection schemes can help improve climate resilience of households and local economies, and also what forms of resilience are affected by social protection programs. And the reason for that, very simply put, is that social protection programs, even if one takes just poor countries, cover a very large expenditure by most governments. And if we can understand better when and under what circumstances and to what extent such programs can promote climate resilience, we have another important tool for which funds are already committed to improve the possibilities for adaptation or resilience to climate change among households that are going to be affected by it. I'll talk a little bit about what social protection programs are, and the relationship and the overlap between social protection and climate resilience. I'll talk a little bit also about a review that we did of work on social protection schemes more broadly, and also how that connects to this particular program I mentioned, the Mahatma Gandhi National Rural Employment Guarantee Scheme. Then I'll then talk briefly about the pathways to resilience that we identified, and then move to presenting some of the results of our work in terms of how social protection programs contribute to household resilience and what they do in terms of effects on local economies. This graph just gives you a sense of the range of social protection programs and the extent of them. The first global map indicates the coverage of social protection programs in 1900. The last one at the bottom right shows what they looked like in 2012. And as I say on the right, on the left, the gray and blue colors on the global map suggest or indicate countries with very low coverage of social protection programs. And the darker green to green areas indicate higher or more dense coverage of social protection programs. And as you can see, between 1900 and 2012, the coverage of social protection programs across different countries has expanded very rapidly and in a very substantial way. There's a lot of variety. So these programs, or this coverage, indicates the sum total of all the different kinds of social protection programs, and it's drawn from the World Social Protection Report or Global Social Protection Report. The two major ways in which one can think about social protection programs is the identity of the recipients. They can be directed towards children, towards older people as pensions, towards those who are disabled, towards for maternal care, or they can be directed towards addressing specific conditions, such as for health or improving illnesses, dealing with crises, addressing unemployment, or simply addressing poverty. So there's a whole range of, and a variety of different kinds of programs. While they're widespread in richer countries in the north, overall levels in poor countries are relatively low. But even so, as this as the set of global maps indicates, there's a rapidly expanding thematic country and population coverage of social protection. And in poor countries, about 5% of the GDP of of these countries is dedicated for social protection program coverage. Globally, just for employment-oriented programs, the expenditures are roughly on the order of about $2 trillion. So, as I said earlier, a very large amount of money is being spent on these protection programs. There are some features that are common between social protection programs and efforts to enhance climate resilience, which are that all social protection programs and climate resilience programs are interested in reducing poverty and thereby reducing vulnerability. They are directed, therefore, towards a common threat. And on the one hand, increasing exposure and sensitivity to climate risks is likely to undermine development gains. By some estimates, more than 100 million households can slip back into poverty by 2030 as a result of climate threats. And on the other hand, social protection programs can support households to absorb and adapt and transform their vulnerability to climate risks and take advantage of new opportunities. And the key strategy or the key strategic need, therefore, is to develop coherent risk management instruments that can be combined with the existing social protection programs to deliver and sustain resilience at different scales. And this is a rough graphic that indicates the three ways in which we are conceptualizing resilience in this work. We talk about absorptive resilience, which is the ability of households or systems to maintain their original structure and function by absorbing relatively infrequent and low magnitude risks. We talk about adaptive resilience, which is the ability of a system or of households to improve their original structure and functions to bounce back from and cope with risks. And we also talk about transformative resilience, which is the ability of systems and households to change their structure to move beyond current risks and vulnerability thresholds. And the two axes indicate the nature of changing risks and the need for different kinds of responses that can allow households or systems to cope with or to adapt to or to transform in the face of these changing risks. This is a very summary graphic for the findings we derived from looking at work on social protection programs and climate resilience, we looked at about a little more than 50 papers, or evidence in a little more than 50 papers, which covered about 65 cases around the world. And the numbers essentially suggest, these are just numerical estimates of how many of these studies identified absorptive versus adaptive versus transformative effects of the social protection programs they covered. And this essentially indicates that relatively few studies identified transformative impacts of social protection programs. Far more of them saw changes happening that could be characterized more as coping or absorption or as adaptation. And we focused on 4 components of these different social protection programs: wages, which are essentially cash wages given for a set of days of employment that many of these programs guarantee to the recipients. We looked at some of the work that is done or produced, or infrastructure that are produced through these social protection programs on the basis of the wages people get. And then some of these programs also incorporate efforts at building skills and retraining or training participants in different occupations than they currently have. And finally, in trying to strengthen institutions through which these different elements of these social protection programs are delivered. And so you might ask why we focused on these 4 components, and the reason is that these are the 4 components that that MNREGA or MGNREGs in India encompasses, and we wanted to see to what extent we can extract findings from the work around the globe to situate what is happening under MNREGA, which is there's a contribution towards wage labor, towards development of rural infrastructure, strengthening of local institutions, and development of skills in new occupations. And I want to say just a little bit about everyday adaptations, which is essentially the idea that people in their everyday lives are always undertaking some changes in response to the stresses that they experience. So adaptation is not necessarily only about developing new infrastructure or implementing large-scale plans to completely transform what people do. It is also what people are doing in any case almost every day in response to many different kinds of risks and stresses that they experience. And trying to understand and trying to emphasize what happens in everyday adaptations, on the one hand, it questions the weight that we often assign to formal adaptation. It tries to undermine the idea that adaptation is painful because, in fact, almost every hour of any given day, you are adapting to something that is happening to you. So the idea that you are doing it painfully, must mean that your life is actually full of suffering and pain, which is what Buddha said, but hopefully that is not the case. It also highlights the continuity of ongoing adaptations that households and individuals and communities undertake with what they will need to do in the future. So there's tremendous inertia as we understand in the climate system. There's tremendous inertia in our infrastructure. There's also tremendous inertia in our social systems, in our everyday behaviors. It's difficult to change. So the success of new adaptation strategies is more likely when they build on existing adaptations that are already going on. And in that sense, combining everyday adaptations with more formal adaptation efforts is more likely to produce higher levels of success in delivering resilience or in enhancing resilience. This slide basically describes how we conceptualized our research and the data that we collected, which is that all the adaptations or all the work that is happening through the MNREGA is happening under different portfolios or different characteristics of climate vulnerability, which are characterized by exposure to different climate impacts and the well-being and sensitivity of different households. And then, as a result of the interventions through MNREGA, through wages, through skill development, through infrastructure, and through institutional strengthening, households' livelihood capitals can change, which then lead to observed outcomes in terms of changes in resilience. And where everyday adaptations fit in this pathways to resilience is in between what MNREGA does and the strategies households adopt to contribute or to build their existing livelihood capitals. So these strategies could be, we have heard about diversification today already. A lot of households diversify their existing assets by adopting or by relying on asset production that is that has where benefit streams from those assets over time are uncorrelated in terms of their risks. Households adopt mobility strategies where they move from one location to another. They also adopt storage to address risks over time. Many of them cooperate across different households. And then finally, where they have access to markets, they can acquire market instruments such as insurance or loans to deal with different kinds of risks that they may face. So instead of going through the entire research process, I want to come quickly to what we found. So as I said, we looked at the different characteristics of vulnerability to climate impacts and different kinds of different levels of sensitivity of households. And our goal was to try to understand how the resilience outcomes that we observed are explained by the relationship between the MNREGA instruments and the changes in livelihood capital. So the two key findings that I would emphasize here are we found that the contribution of MNREGA through wages and through public infrastructure is closely associated with changes in livelihood capitals that are natural capital and financial capital, and they are most commonly associated with absorptive resilience that households undertake. So roughly about 34% of households in 4 states in India that we carried out research in described themselves as having experienced absorptive capacities, or instead of completely changing their existing occupations or changing their livelihood capitals, they're able to cope with or deal with existing climate impacts that they experienced. And then in a similar way, where there was some convergence between MNREGA efforts at providing wages and public infrastructure and other existing programs, but there was a very strong, very substantial external exposure to climate risks. This contribution from MNREGA, or from a social protection program, was inadequate to enable households to cope with or to maintain their existing livelihood strategies, and they underwent or they experienced a decline in their well-being. And finally, where households were able to get access to and take advantage of all of the different MNREGA components, they saw an improvement in the physical capital, social capital, human, financial, and natural capital, and they were more able to adapt or to transform their existing livelihood portfolios to deal with climate risks or to undergo adaptive or transformative resilience. Taking these findings and representing them very quickly across the different states and for the different kinds of experienced climate impacts, what we find is that absorptive resilience was experienced by households that were typically exposed to cyclones and which were able to access and take advantage of MNREGA. Adaptive resilience was experienced by about 26% of our households. They were exposed primarily to low magnitude, long-lasting droughts. Transformative resilience was experienced only by about 4% of the households, and it typically happened when MNREGA implementation occurred together with other government interventions in the local arena, and then 19% of the households, despite some exposure and being able to access MNREGA benefits, were not able to maintain their existing their existing levels of well-being. And these were the households that experienced droughts over a long period of time and very substantial droughts. When we look at the households themselves, we find that lower well-being households are more likely to be able to only experience absorptive resilience, and higher well-being households more able to experience and undertake transformative resilience. We also carried out some analyses that differentiated between the experiences of women versus men in the households, and men reported more often that they were able to absorb and lower well-being men reported more often that they were able to maintain or adapt or transform their abilities. Women more likely to report a decline in their resilience. And then both men and women were equally able to experience absorptive resilience. So, and then we also looked at how Manrega, or what Manrega's contributions to the local economy were. In this case, we essentially see that Manrega contributed to improvements in the local labor markets, or to maintaining the local labor market wages. It was also able to improve or maintain climate infrastructure, and it was also finally able to enhance agricultural productivity as reported by households. So our key findings are social protection programs based on the analysis of the relationship between Manrega and the households that are covered by it. It contributes to the climate resilience of approximately 64% of the households we covered. I didn't say actually our total surveys a sample size. We interviewed approximately 620 households in 4 states in India. So it contributes to the resilience of about 64% of households. It contributes also to the resilience of local economies. The extent of its contribution depends on the exposure of households to different kinds of climate shocks and their sensitivity in terms of their initial levels of well-being. Rapid onset shocks are more likely to lead to absorptive resilience, especially when these are low-level shocks or medium-level shocks and don't last for a long time. Slow onset shocks are more likely to enable social protection programs to contribute to adaptive resilience, again, when these shocks are of a low magnitude. And frequent and high magnitude shocks, as in the case of drought in Jharkhand, households experienced a decline in their ability to cope with climate risks despite receiving benefits from Manrega. So overall, we can say on the basis of the work, that we did, that for Manrega, access to guaranteed wages and public infrastructure for natural resource management or dependent households enables them to absorb or to bounce back from climate impacts. Adaptive resilience is more likely to occur when households are able to take advantage of all the 4 different components of Manrega, and they are related to households being able to strengthen their livelihood capitals and improving their livelihoods. And finally, transformative resilience is relatively uncommon, similar to what we saw in the existing literature from other countries. It requires significant investments in new kinds of livelihood capitals and new forms of training and skill development for households to be able to move beyond their existing thresholds. Social protection programs, when they are in convergence with other programs and they're able to provide non-climate sensitive investments like access to renewable energy, they are more likely to also enable transformative resilience. And finally, where you have high exposure of households to resilience and when their initial levels of well-being are low, there's a clear trend towards a decline in their existing levels of resilience. Finally, for social protection programs, which are a promising instrument to improve existing levels of resilience of households, their contribution to such improvements will hinge on a more coherent approach, a more coherent marriage of different risk management strategies which emphasize convergence with other existing policies, development of new skills, and more comprehensive coverage of households that benefit from these programs. Thank you very much.
Okay, our final speaker in this session is Praveen Kumar. He is the Lovell Endowed Professor of Civil and Environmental Engineering here at the University of Illinois. His research focuses on complex hydrologic systems bridging across theory, modeling, and informatics. The title of his talk today is Role of Technology in Adaptation to Climate Change. Thank you.
Thank you. Can I take a moment to reorder a slide? I'm good. Go to the top. Okay. Thank you. Sorry about that. So everybody has been sitting here for the whole day. I'm sure you're tired. So I'll try to keep it short. So I'm going to try and talk about the role of technology in adaptation to climate change. So the first thing I want to do is just take a few examples from the past and see what we can learn. So 2 weeks ago, I was in Netherlands. And as many of you would know, Netherlands is a country where 2/3 of the country is below sea level, about anywhere from 3 to 5 meters. And in 1953, on 1st February and 2nd February night, they experienced a major storm surge. And there was a North Sea wind, which basically forced the water down the delta. And about 1,800 people died in that storm. And the society as a whole basically said, never again. And that was a major policy determination, a societal value. And they have been living with the possibility of flood as a reality for a long time. But they have developed infrastructure over the last 40, 50 years, basically to combat floods, particularly storm surge, but also the possibility of river flooding. So what you see down on the lower left-hand side is an infrastructure on the Rhine. This is the port of Rotterdam, which is one of the busiest ports in the world. And that particular structure basically is an arm which opens and closes. And there is no human intervention on the determination of when that will happen. It's all driven by data that is coming out from the sea and everywhere else, and models and prediction. And essentially, it's all programmed, so there is no human intervention. There isn't a possibility that somebody will request that, wait for another 2 hours, let my ship in, or so forth. It's just driven completely by information. And in the last 20 years, they've had to close it once, or the computer closed it only once. So the structure is basically generally open to allow ships in and out in this very large port, but they are trying to protect against storm surge. And that is a real concern under climate change. So at this time, they are putting in a margin of a 1 meter rise in sea level so that they are still protected, and that they think is a good guide for the next until 2050, and then we'll see what happens after that. The figure on the other side, which is again a storm surge protector, is basically a vertical protection. And this generally left open to basically allow mixing between the fresh and the seawater, because there are a lot of aquatic ecosystems that need to basically be protected because of that mixing. Otherwise, they would lose a lot of the wildlife in that environment. So this is a country where basically is very determined to combat climate change. And they are anticipatory, and they put in a lot of very deliberate effort so that never again mantra holds. Another example, this is Cyclone Phailin in October 2013. It was a Category 4 hurricane or cyclone or typhoon, as your preference. It hit India. There was another cyclone that hit India in 1999 when 10,000 people had died. And basically the states in that region decided to take a zero casualty approach. And over a period of time, they developed technologies, communication technologies, and other facilities so that they can evacuate the people. And when the storm hit in 2013, 9 million people were affected. About 900,000 people were evacuated. Now remember that this is a population which is very tribal, very in villages. There are some cities in there, but by and large, the communication is a big challenge. How do you get information to the people who are very distant from the cities? But all that was done, and people were evacuated, and only about 38 people died as a result of this major hurricane. So it took years of planning. It required construction of disaster risk mitigations infrastructure, setting up of evacuation protocols, identification of potential safe buildings, working with communities and local organizations, and establishment of evacuation routes, and focusing on early warning systems to make sure that they can actually implement this. The reliability of prediction was also a very important concern, so that they could actually monitor the path and predict way in advance so that they could evacuate. So in that context, when I was looking at Hurricane Irma and Harvey, there was a great effort in Florida to evacuate. And to the extent possible, there was a lot of accommodation. But what troubled me a little bit was this picture on the left-hand side, where we see the vehicles trying to leave. I'm sure it was a parking lot more than a road. But the other side of the road is pretty empty. You hardly see any vehicles. And there were reports that the governor of Florida, who did a great job, said basically they left it open for emergency vehicles and things like that. I'm pretty sure there could have been more done to open up a few more lanes on the other side so that evacuations could have been done a little better. So in my mind, I don't think this has been thought of enough. And to some extent, while the preparedness happens very rapidly, because we can afford to do that, there more can be done. So the key point in here is that having a reliable early warning system is a very important aspect of adaptation, and accurate prediction is also part of that challenge. So most of the time when we talk about climate impacts, and we have heard that throughout the day today and yesterday, we take an alarmist approach, basically saying that, well, extremes, floods, droughts, and all the other things that happen. But the change that climate is bringing happens in some very subtle ways as well. So just yesterday, we published a paper in Nature Scientific Reports, and this is an NSF news report on changes in non-extreme precipitation. So when you're looking at daily precipitation, are the patterns in daily precipitation changing? Are the high-frequency rainfall patterns that you see almost every day, not the extremes, are they changing? So when we look at average daily precipitation, so this is all rain gauge data. There's no model or any massaging of the data. And you look at trends. So what you see in blue is essentially that average daily precipitation trends are positive, and in the red, they are negative. So this is pretty consistent with what most of the climate models will give you, and almost this is used for a lot of the climate model validation and characterization. However, rainfall variability is not just daily precipitation, it's the frequency of rainfall, the length of rainy period, and so forth. So when you start adding more subtlety to the variability of precipitation, what you start seeing is that there is more detailed changes that are happening. So what you see in blue is, you can think of the probability of a rain event in a particular year. And the darker the blue, the higher the probability, right? So the probability of a rain event happening is getting higher in some areas, and the red is the opposite. It's decreasing. And what you see is an intermixing of those red and blue. So it's not always that you can rely on the magnitude of precipitation to tell you the entire story. So you can do this analysis, and you can do a trend analysis on daily precipitation or a higher threshold. And so we looked at different thresholds, and what you see is the right side of that graph is the 95th percentile. That's the extreme events, and we are talking about changes in extreme events. But the trend in that is really small. But if you look at the high-frequency rainfall events, the daily rainfall events, or the 25th percentile or the 50th percentile, the trends in them is large and more variable. And so both in terms of the probability of rainfall and the length of a rainy period. in the number of consecutive days. So that's a more subtle variation of climate change. This is historical data. This is 50 years of analysis, or rather greater than 50 years of analysis at any of the rain gauge sites. And so, as I said, I mean, there is a lot of intermixing and you don't get a complete story. Why is that? So you can take this data and put it on ecoregions and try and understand the subtleties as to why that is happening. And if you won't be able to see that detail in this particular map, but if you examine one of the details, say in the northwestern US, you see that the changes are very linked to microclimate and ecosystems. So biomes and the microclimate that they generate determine whether you're going to get a change in positive change in precipitation or a negative change in precipitation. So the climate change impact is far more subtle than what we are presently thinking of. And these will have long-term impacts. They can have potential creeping impacts. And when you're talking about tipping points, we may not realize when we have hit the tipping points because we are not paying attention to a lot of these aspects of change. So when we think about the climate change and adaptation needs, we think about things like temperature in terms of magnitude. We need to distinguish between summer and winter, which a lot of us are doing, in terms of frequency, heat and cold waves. When we are thinking about precipitation variability, we don't think about generally the vast subtleties of that in terms of magnitude, frequency, timing, duration, and sequencing. We have talked about CO2 concentration, the way it impacts or the acclimation of vegetation. And we've talked about melting of ice caps, glaciers, and permafrost. So when you're thinking about water adaptation needs, we need to take a much broader look in terms of water resources, protection against extremes, agricultural productivity, ecosystems, and human infrastructure. And many of these things we have talked about. So the real question is basically, how do we start to basically see our world in more detail, in more subtle ways, so that we can be able to manage these things, not at the gross scale that we have been talking about, but in a much finer, nuanced way. And so the technologies for doing that are becoming available. So what you see on the top right is basically LiDAR map and of vegetation from the Carnegie instruments, and they can fly that at very high resolution, and that's the carbon uptake. This was published in National Geographic a couple of years ago. And the lower left, what you see is a very detailed characterization of stream channels. So with our ability to be able to see these details, how do we then start folding this information into our ability to predict and model, and then develop strategies for understanding the science and adaptation and mitigation strategies? So I lead an effort called the Critical Zone Observatory. We are part of an observatory network across the country, funded by the National Science Foundation. And we have 2 primary sites, one in Iowa and one here in Illinois. And we partner with another site in Minnesota. So we have been studying essentially what is called the critical zone. This is the zone from the top of the canopy to below the groundwater table, to understand this holistically and then expand out spatially to watershed and larger scales, and basically transfer this information to understanding of all the processes that are going on in there. And in the process of doing that, we have basically taken advantage of a variety of technologies, from airborne instruments to putting in fiber optic cables deep underground. And these instruments allow us to characterize our landscape in unprecedented details. And I'll show you some examples. The question that we ask is, how can you use all this information to inform the science, and how can you make that science useful? So one example is that when you look at the landscape, we think of Illinois as flat, and it is, but within that, there are some subtle topographic variations. So that's a picture I took from a plane in spring. We had a very wet spring. And as a result of that, you can see a lot of the microtopographic depressions. And it wasn't clear to me if that has any impact on productivity of agriculture. And then 2 weeks ago, when I was flying back from Netherlands, I took another shot. And not at the same location, but what you do see is basically variations in the productivity. So my plant biology colleagues can tell me whether that is actually a difference in productivity or not. But nevertheless, it appears that if we are trying to achieve a certain percentage through genomic characterization of plants, I think we can do a little bit more in trying to manage our heterogeneities in the landscape. So in our group, we have been developing some models, basically to be able to understand what goes on in these microtopographic depressions and how do these basically affect the productivity, the hydrology, the biogeochemistry, and so forth. So this is one technology, the LiDAR, which gives you information about the topography in a lot of details. The LiDAR can also give you the vertical vegetation profile and structure. It can help you characterize the landscape. You can get hyperspectral data, that's on the left, bottom left. And new technologies such as waveform LiDAR have become available, and they can help resolve forest canopies in unprecedented detail, far more than I showed you before. And so if you essentially zoom down, so that's an Allerton forest there. And if you zoom down to one tree, you can see basically with these technologies an amazing amount of detail in there. So just focus on the left-hand side. That's basically the light penetration through the canopy, and it's the reflectance, and the structure of the canopy is revealed. So can we model these canopies or take advantage of the information that is being available to characterize photosynthesis, to characterize the impact of carbon, CO2 fertilization, and nitrogen? I'm already done? Okay, thank you. So, and here we have results from a hyperspectral instrument, and again, it's the same area. And each circle is a tree, which we can identify, and each color is a different species of tree, which we can identify. So, and then we can do vertical characterization of trees as well. So if we can get this thing, we're trying to get to the modeling of this. And so I think I should quickly look at the model. So I won't go bore you with the details of the model, but the key idea here is, given all this information and very, very high resolution from LiDAR, from hyperspectral instruments and other technologies, how do you actually characterize the landscape and the processes associated with that? So as you can imagine, these models are pretty complex. We run it on blue waters. But what you start to see is unprecedented details of simulations. So these are 1 meter pixels, that's what you see, and uniform rainfall. So any variation you see in the soil moisture is essentially driven by topography and vegetation in there. So you can actually see how just the farming practice induces certain variation in soil moisture. And you can then use that to understand what will be the impact of climate change, where will it impact soil moisture, under which crops, and so forth. So that's a characterization where we looked at projected climate CO2 in the atmosphere. So you have S2 at 550 ppm and S3 at 550 ppm, and you can look at the differences. And across the landscape, you can see the impact of microtopographic variations on soil moisture and plant productivity. We can take it even further, and we can look at nitrates or various species of nitrogen in the soil, both in terms of concentration and age. And the impact of tiles on how the landscape, how the variation in concentration and weight varies across the landscape. So the question is, why do you want to care about nitrogen in a climate change story? 2 reasons. First of all, the environmental concerns of nitrogen. But the second concern is that the application of nitrogen fertilizer is one of the largest energy users. So there is an embodied energy that goes into nitrogen fertilization, which is very large. And 50% of the agricultural, first of all, agriculture is an energy intensive effort. and 50% of that energy is embodied energy in nitrogen. So if we can optimize nitrogen fertilizer application on the landscape, we basically reduce the carbon footprint. We are in an era where the resolution is increasing even more. This is a landscape at 15 centimeter resolution taken from a drone. The question is, why do you care about it at that resolution? I talked about very subtle variations in precipitation due to climate change. One of the possible changes is in drop size distribution. People have talked about intensified rainfall events and so forth. The drop sizes essentially break up the soil and release the carbon and cause erosion. So you have erosion of soil and carbon from these landscapes. The question is, can you understand that and predict it at that level? So my colleague Thanos Papanikolaou did some work related to how the carbon stored in the soil has changed over time. And what you see in that green curve is as the agriculture practices have changed, the carbon stored in the soil has changed. It's now recovering because of conservation practices. But as the soil stores an enormous amount of carbon. And when we link that to rainfall variability and change and its impact on soil and loss of carbon from the soil, that can be an enormous concern. And so it is important to do that. I'm going to skip this slide. Okay, so basically, in summary, what we need to think about is that climate change impacts can be subtle, but with significant consequences. And the adaptation requires feasibility of our technologies, both in terms of observational, communication, as well as our design, our infrastructure design. And there needs to be a societal buy-in, and we have discussed a lot about communication to get this societal buy-in. Emerging technologies offer unprecedented opportunities to address a variety of approaches for adoption. And my appeal to is basically to think about this challenge as a holistic challenge. We need to address them across the entire range of scales and of variabilities and spatial scales, not just think about real big questions. I mean, just think about hypoxia problem. It arises in our farmlands and creates a large scale impact. We cannot address that at the large scale. We have to address that at the source. And that would be the case for most of the climate adaptation and mitigation strategies. With that, I'll stop. Thank you very much.
So yeah, we have a little bit of time for questions from our remaining speakers, if we can get them up here.
I've got a question for each of you. Mark, maybe you could correct my memory, but I seem to recall the benefits from this package you were proposing were about 4% of GDP. So current GDP, apply that 4% to current world GDP, it's about $3 trillion. The costs of achieving that were only on the order of 30 billion. So it seems like it's a factor of 100 there between the benefits and the costs. Am I missing something, or is it really that good a deal? The package I didn't kind of fully capture all that, but it looked like really big benefits from that package.
Yeah, I mean it is. I mean this is linking with CGE model. So we're looking at the changes in that. I could go back and look at that 4% number, but yeah, it came out as a very very large impact. So, yep.
Praveen, this is amazing stuff. This 15 centimeters. I was trying to think how much that really fine resolution. I mean, are you teaming up with the precision ag people to? I mean, this is at the level, an even finer level, I think, than they're dealing with now. You have the kind of information which could really inform management in a very specific way. Are you I didn't hear much about precision ag in this context, but it could have big environmental benefits, productivity benefits. You alluded a little to that. Could you say something more about that?
Yeah, sure. So first of all, we have data at 7 centimeters, just to amaze you. I just couldn't put it because the file was too large. But having said that, I would be very interested in teaming up with precision ag people, because there is a significant opportunity in terms of management of resources and application in there. This is just fresh off the press, so it'll just be a little bit more time on that one.
Thank you so much. It's a question for you, Praveen. So I'm very impressed by the spatial scale that you are using, obviously here. As you may be aware, socioeconomists on our side, it's very hard for us to get data below, say, county level, because very little exists and time series are not long enough otherwise. So my question is this. I think at the end of the day, the goal is to provide some climate change adaptation recommendations. So how do you offer to reconcile the fact that you're using such a fine scale and that for any socioeconomic data of any sort, obviously the scale is going to be way bigger, county level type. What can be done, in your opinion, to optimize that combination of scales?
Yeah, no, that's a good question. So right now we are focused on questions related to process as to what can we understand at that finer scale. And there will be a real question on how do you actually then implement this further into essentially an economic scale, a county level, and things like that. We haven't addressed that, but that's a good question. But right now we are focused on what is this data useful? What kind of processes can we understand? What does it tell us as to what's going on? And once that is done, then, once it's done and it's established that this is useful, I'm sure there will be other convergence that will make that possible.
So Praveen, from the data that you showed, you can really zoom in on the land use and see where there are trees and where there are crops, and I guess which types of crops and so on. So currently people use like this cropland data layer to do this. That's sort of our best at the moment in terms of figuring out. And there's a lot of uncertainty about just being able to look from the satellite images and be able to distinguish between the green stuff. Is it hay, pasture, cultivated, grassland, what type of grasslands? So is this something that would improve those images, our capability of understanding how to distinguish between different types of land uses, and how large a scale could this be implemented at?
Yeah, so as I said, we're focused on process and feasibility. So a lot of the analysis that was done was basically using data from airplanes. And these are very, very high resolution, 1 meter resolution for both vegetation and the land. Satellite data don't get there in terms of there is plans to fly JEDI, which is basically a LiDAR satellite, which will probably give us 30 meter data. Kunshan, you're here, is that right? 200? 25 meter. So we can potentially get, if that flies, we can potentially get LiDAR at 25 meter resolution. So we can ask questions from these high resolution as to what will be lost if you go up to a satellite scale. We have done that with hyperspectral, and some of these are scalable in some properties, and we're trying to identify as you scale them up how much more uncertainty is used. So it still remains at the forefront of the science on what can be done. But as I said, if we establish that this can work, then I think there will be other approaches that will have to come to make this digestible on a larger scale.